Hello everyone. Today I'm going to give you the most easy to understand yet the most effective explanation on the photoelectric effect for A-level physics syllabus, whether you're doing AQA, Edexcel or OCR or any. This is going to be a very useful tutorial. So let's get started. Let's try to simply understand what is meant by photoelectric emission. If light above a certain frequency is shown on a metal and electrons are ejected from the metal, we call this process photoelectric emission. The electrons ejected from the metal are called photoelectrons. Photoelectric effect can be understood by the gold-leaf electroscope experiment. Gold-leaf electroscope is shown in figure 1. This consists with a disc, a metal stem and a gold leaf attached to the end of the stem. This can be charged using electrostatically charged rod as shown in figure 2. The charged rod is touched on the surface of the disc and some of the charges are transferred to the electroscope. Once it is removed, the charges will be distributed all over the electroscope as shown in figure 3. In this figure, the negative charges on the gold leaf will repel on the negative charges on the metal stem. As a result, the leaf will rise. This is same for the positively charged electroscope. Now suppose the photoelectric effect we talked earlier will take place on the negatively charged metal plate on the gold leaf electroscope. When light above a certain frequency is shining on the metal, some electrons are removed from the metal. Now the negative charges on the gold leaf will transfer to the metal to fill the lost electrons. Since the gold leaf lost some negative charges, the repulsion is not much stronger like before, so the gold leaf will fall. Now let's have a look on some observations. When intense red light shone onto a negatively charged zinc plate, the gold leaf did not fall, or, in other words, no change. But when UV light shone onto the same system, the gold leaf fell. This means some electrons ejected from the plate or discharged due to the UV light. This shows that the plate will only discharge if the frequency of the light is greater than a particular value. In this example, UV light exceeds this value where intense red light does not. It is important to highlight that the frequency of the light made the difference, but not the intensity or the brightness. Vacuum photocell experiments are very much important to quantify the values like how much photoelectrons were ejected due to the photoelectric effect or the kinetic energy of the photoelectrons. A vacuum photocell is a glass tube that contains a metal plate referred to as the photocathode and a smaller metal electrode referred to as the anode. The microammeter in the circuit can be used to measure the photoelectric current, and this is proportional to the number of electrons per second that transfer from the cathode to the anode. Let's have a look on the observations in a vacuum cell photoelectric experiment. Emission of photoelectrons only occur above a particular frequency. If the light is less than this frequency, no matter how much the light is intense or bright, photoelectric emission does not take place. If photoelectric emission is taking place, the number of the photoelectrons are directly proportional to the intensity of the light. Photoelectrons are emitted instantly without any delay as the light falls on the metal. When the photoelectric effect was first discovered in 1887 by the scientist Hertz, the physicists of the time could not solve this phenomena. They couldn't fully explain it using the wave theory of radiation. Let's now see why the wave theory could not explain photoelectric effect. Why photoelectrons were not emitted at any frequency even after increasing its intensity. According to the classical wave theory, the intensity of a light wave is proportional to the square of its amplitude. And we also know higher amplitude of a wave means higher energy it carries. So according to the wave theory, the photoelectric effect should take place at any frequency of light, provided that the light is intense enough to supply the energy needed to eject the photoelectrons. However, observations show that the photoelectric effect does not occur even though the intensity is increased for the light that is less than a particular frequency. The second question is why photoelectrons were emitted without any delay. In the classical wave theory, the light energy is uniformly distributed over the wavefront. So when the light falls on the metal, the energy of the incident light will not entirely go to a particular electron in the metal, but will be distributed uniformly to other electrons also. So the electrons will take some time to accumulate enough energy to escape from the metal surface. Hence, there should be a measurable time lag between the impinging of the light on the surface and the ejection of photoelectrons. However, no time lag is observed. Photoelectrons are ejected the instant the light falls on the metal. We understood why wave theory could not explain the behavior of the photoelectric effect. However, Albert Einstein did so by inventing a new theory of radiation called the photon model. His key idea was that the electromagnetic radiation or light consists of photons. In other words, wave packets or energy packets. The energy of a photon is directly proportional to its frequency and therefore its energy is equal to hf, where f is the frequency of the radiation and h is the Planck's constant. Einstein's photon model showed that energy is quantized and can be considered as particles rather than continuous waves. A completely new way of thinking about energy. Now let's think about the photoelectric emission using the photon model. We observed when the red light shone onto a metal, photoelectric effect did not take place. This is because the energy carried by the photons at the frequency of red light is not sufficient to knock off the electrons on the metal. We also observed when UV light is shone onto a metal, photoelectric effect occurred. This is because the energy carried by the photons at the frequency of UV light is sufficient to knock off the electrons on the metal. Let's try to simplify this more. Frequency of UV light is much higher than the frequency of red light in the frequency spectrum as shown in the figure. Since energy is proportional to the frequency, the energy of UV light is much greater than the red light and therefore UV light can knock off the electrons from the metal surface but red light cannot. Let's understand the term work function in the photoelectric effect. Photons provide energy to electrons to eject from the metal surface. One photon can give energy to one electron. The energy needed by electrons to eject completely depends on the type of metal. The minimum energy or work required to eject an electron completely from a metal surface is called the work function. Therefore, the energy of a photon should at least equal to the work function of the metal in order to photoelectric effect to take place. The energy of a photon should be greater than or equal to the work function to produce photoelectric effect. Let's understand the term threshold frequency. All the time in this explanation we talked about a particular frequency that should be exceeded by photons in order to happen the photoelectric effect. This frequency is called the threshold frequency. Energy of photons should be greater than or equal to the work function in order to produce photoelectric emission. Work function can be given as Planck's constant times F naught. The energy of photon is given by hf, which is greater than or equal to hf naught. Now if we cancel off H term, we get frequency of the photons should be greater than or equal to F naught, and this F naught is the minimum limit of frequency of photons to produce photoelectric effect. We call this threshold frequency. Threshold frequency, in the most simple words, the minimum frequency of photons or light which will produce photoelectric effect. Einstein developed an equation to describe the photoelectric effect, which is based fundamentally on the energy conservation. As we discussed earlier, the electrons gain energy from the photons to escape from the metal. The minimum energy they should gain to escape from the metal is equal to the work function. Now, what will happen to the excess energy, or the difference of energy between the photon and the work function? This will be used by the electron to gain the kinetic energy. Now we can write an equation for the total energy conservation. Photon's energy is equal to the maximum kinetic energy of electrons plus the work function. Therefore, the kinetic energy that electron can have on departure from the metal surface is less than or equal to the difference between photon energy and the work function. This maximum possible kinetic energy determines the maximum velocity of photoelectrons. The maximum kinetic energy of the photoelectrons emitted for a given frequency of light can be measured using a photocell. If the measurements for different frequencies are plotted as a graph of maximum kinetic energy against the frequency of light, a straight line of the form of y equals mx plus c is obtained. This is in accordance with the above equation as y is equal to the kinetic energy maximum and x is equal to the frequency of light. Note that the gradient of the line is equal to the Planck's constant. The y-intercept is equal to the negative work function and the x-intercept is equal to the threshold frequency. Let's see what is meant by the stopping voltage in photoelectric effect. Electrons that escape from the metal plate can be attracted back to it by giving the plate a sufficient positive charge. The minimum potential needed to stop photoelectric emission is called the stopping potential and denoted by Vs. At this potential, the maximum kinetic energy of the emitted electron is reduced to zero because each emitted electron must do extra work equal to electron's charge E times the stopping potential Vs to leave the metal surface. Hence, its maximum kinetic energy is equal to charge of electron times the stopping potential Vs. I hope in this video you understood all the concepts related to the photoelectric effect. If you like this video, please give a thumbs up and leave a comment, and please subscribe for more videos. Thank you.